Hello, I'm Szymon Toruńczyk from the University of Warsaw, and I will be presenting joint work with Thomas Zeumer from the Ruhr University in Bochum. The topic of this paper is register automata with Extrema constraints and an application to two-variable logic. So I'll start with stating the main results of the paper, and then I will explain what they mean and how they are proved. So the first main result states that satisfiability of two-variable logic with two linear orders is decidable. And the second main result is about a model of register automata, which are actually used as a tool for proving the first result. These automata are tree-register automata with Extrema constraints. And they process infinite trees where every node is labeled by a data value, which is a real number, and the automaton can store those data values in its registers and compare the values with respect to the total order of the reals. Moreover, the automaton can access at any point, at any node of the tree, it can access the supremum or the infimum of some values in the subtree rooted at a current node. So let me start by explaining the first result. So the first result concerns two-variable logic. So two-variable logic is the fragment of first-order logic where you can just use two variables, but you can reuse them. So for example, you can write a sentence expressing that every node X has a node Y, which it is related by the R relation, but this node Y has some other node, which we also call X to reuse the variables, with which it is not connected by the R relation. And this has to satisfy universally, so this X must have a Y with which it is connected by an R edge, and this Y must have some X with which it is not connected by an R edge. So here, for example, I have drawn a model of this sentence. The satisfiability question asks, does a given sentence of two-variable logic have a model? And this was solved by Mortimer in 1975, who showed that two-variable logic has the finite model property, which means that if a given sentence has a model, then it also has a finite model. And this gives two semi-procedures for deciding the satisfiability of a given sentence. One semi-procedure scans through all finite models and checks whether one of them satisfies the sentence. And the other semi-procedure scans through all proofs that the sentence is contradictory. And by Gödel's completeness theorem and Mortimer's result, exactly one of those semi-procedures will terminate in finite time. So this finite model property yields the decidability of the two-variable logic, and also the finite satisfiability of two-variable logic. So the question, does a given sentence have a finite model? Those two questions turn out to be equivalent in this case by Mortimer's result. Two-variable logic is quite restrictive. It cannot express, for example, that a given relation is transitive. Indeed, if we consider two-variable logic with a binary relation which is assumed to be a total order or linear order, then this logic no longer has the finite model property, because we can write a sentence that every node X has a node Y which is larger than it. So if this relation is a total order, then this enforces that the order is infinite. So there is an infinite model, but there's no finite model, so the finite model property fails. In particular, this shows that one cannot axiomatize that a binary relation is a total order or is transitive. Yet the satisfiability of the two-variable logic with a linear order is still decidable, as shown by Otto. And there are other results in this spirit. For example, the two-variable logic with two equivalence relations has decidable satisfiability. The finite satisfiability of the two-variable fragment with one transitive relation is also decidable by result of Pratt-Hartmann. Very related to this work is the result of Schwentig and Zäumer, which states that finite satisfiability of the two-variable fragment with two total orders is decidable. So we are given two binary relation symbols, and we assume that they are total orders, and we ask, does a given sentence of two-variable logic have a model, a finite model, in which those two relations are total orders? So this problem was shown to be decidable, but Schwentig and Zäumer posed the question, does the general satisfiability, is it decidable? So can we decide whether there's an arbitrary model, not necessarily a finite one, of a given sentence, talking about two total orders? And this is our first result. So the result states that general satisfiability of the two-variable logic with two total orders, plus additionally some other relations, is decidable. So again, we're given a sentence phi. It can talk about two total orders and some additional relations, and it uses just two variables. And we want to decide if this sentence has some model in which the first two relations are total orders. You can express this more concisely by stating that the satisfiability of existential second-order logic with two variables and two linear orders is decidable. So in this existential second-order logic, we can use many second-order variables which range over relations, and then we can write a sentence of the two-variable fragment which uses only two first-order variables and talks about two total orders and the quantified relations. So this is what the first theorem states. And the way it is proved is by a reduction to the automata model, which is considered in the second result. So let me start by describing the reduction. In this special case, if we just consider finite satisfiability, which turns out to be actually easier in this case. So this reduction gives an alternative proof of the result of Schwentig and Zäumer. So this reduction is based on the following simple observation that a structure with two linear orders can be represented as a word in a certain way. So here's a structure with two linear orders and also some unary predicates, which are represented by three colors. Such a structure can be visualized as a set of colored points on a plane, and the first order corresponds to the horizontal order, and the second order corresponds to the vertical order. And to represent this as a word, first assign values to the y-axis, and then process the points from left to right with respect to the first order. So first we have an A-labeled node with value 5, then we have an A-labeled node with value 6, then a C-labeled node with value 3, and so on. So what we get is a data word where every position carries a symbol from a finite alphabet, as well as a value from which is a natural number or real number, or a value from a totally ordered set. And observe that in this word, no data value occurs twice. This is because we assume that the second order is a total order and not a pre-order. Conversely, every data word of this form, where no data value occurs twice, corresponds to a structure with 2 total orders and 3 colors. This correspondence can be used to reduce the satisfiability problem, the finite satisfiability problem, of the 2 variable fragments with 2 linear orders, to a problem about register automata. To do this, first we rewrite the formula phi in a special normal form, known as Scott normal form, which is a conjunction of sentences of the form for all, or for all exists. So a typical sentence of the form for all says, no A has a B which is to the northeast of it. This can be expressed as a sentence with 2 universal quantifiers. And how do we verify this on the data word representation of our structure? Well, we can process the word from left to right and remember in a special register the minimal value of a node with label A. So we go from left to right and we see a node with label A and value 5. We store it in our register and we move to the right. We see another A with larger value, so we keep our 5 unchanged and we proceed to the next position. And we continue, and whenever we see a B which is larger than the minimal A encountered so far, this means that our constraint is violated. So the automaton can verify that this constraint, whether this constraint is violated or not. Now let's look at a typical constraint of the form for all exists. So here's a constraint which says every B has some A to the southwest of it. And we observe that we can use the same register to verify this condition. Whenever we see a B, we check that its value is larger than the value stored in the register. So here we had a 7 and it's larger than 5, so this means that the condition is satisfied by this B. Here we see an A, so we update the value in the register, so that now the minimal value is 1. Now we see a B with value 4, and it's larger than the value of some A to the left, and the same for the last B. So I hope this gives some intuition how a register automaton, which can store the data values in its registers and compare them with respect to inequality, can verify the constraints in Scott normal form. In order to do this, we need registers storing the minimum and the maximum of values with label A to the left and to the right from a given node. And those values can be verified by non-deterministic register automaton. So it is easy to see that if there is a finite model of the sentence, then the data word representation of this model is accepted by the automaton. Conversely, if we have a data word which is accepted by the register automaton, and in which no value appears twice, then this data word represents a finite model of our sentence. So to close the loop, it suffices to show that if there is some word which is accepted by the register automaton, then there is also a word which is accepted by the automaton and in which no data value occurs twice. Essentially, if some data value occurs twice in the word, then we can perturb the data values slightly and still obtain a word which is accepted by the automaton, but where the 2 values are distinct. This requires an analysis of the form of the automata which we construct here. So this essentially gives a reduction of the finite satisfiability problem for the 2 variable logic with 2 linear orders to the emptiness problem of register automata over data words with linearly ordered data values. And this emptiness problem is easily seen to be decidable, so this gives an alternative proof of the result of Schwentik and Zollner. Now, if you want to generalize this approach to general satisfiability, we need to be able to consider data words or other structures which are infinite. So a natural approach is to consider omega words equipped with data values, but this only allows us to consider structures where the first order has the type omega. So in particular, it's a discrete, well-founded order. Nevertheless, we can consider this case where one order is of type omega, and in order to follow the path outlined earlier, we need register automata on omega words, and these automata should be able to access the supremum and the infimum of certain values which occur to the right of a current node. We have a set of positions, and the automaton is at a current node, and in this node, it can consider, let's say it's y, it can consider the set of all values at nodes which are labeled A and which are greater or equal than y in the horizontal order. So each value here, each node here has a value. And we look at the ones to the right of y, which are labeled A, and we take the supremum of the values there. So this is what the automaton can access this supremum when it is placed at node y. It could also look at the minimum of the values to the left, but this it can compute in the usual way by just updating the current minimum when processing the word from left to right. So we only need a special feature which allows to access the supremum and the infimum of the value to the right. These numbers have to take values in a domain which is closed under taking suprema and infima. So for example, the reals with their order. So once we show that this model of automata has decidable emptiness, essentially the same reduction as sketched earlier allows us to solve the satisfiability problem for the two-variable fragment, where one of the orders is assumed to have type omega. Note that any such structure needs to be countable, and then in particular the second order is a countable order, so it embeds into the rationals, and in particular it embeds into the reals. And this is why we need to take our data values to be the real numbers. In general, observe that it suffices to consider countable models, since if a sentence has a model, then it has a countable model by the downward Leeuwenheim-Skolem theorem. And for countable models, observe that any linear order embeds into the rationals with their linear order. And here's an observation dating back to Rabin, that the dense linear order is the same as the left to right order in the complete binary tree. So here are the nodes of the complete binary tree. And we can say, for example, that this node is x is to the left of y, and also this node x prime is to the left of y. So there's a natural left to right order on the nodes of the complete binary tree, and this order is dense, and hence is isomorphic to the rationals. So this suggests, and this is the idea used by Rabin, to consider binary trees if we want to study linear orders, countable linear orders. And in order to make this idea work, we need register automata which process infinite trees, infinite binary trees, whose nodes are labeled by elements of a finite alphabet as well as values from the reals. And those automata are equipped with registers, which can be compared for inequality. And also at any given node, the automaton can access the supremum or the infimum of all the values associated to descendants of the current node with a specified label. So this is roughly the automaton model that we need. And using this automaton model, we can proceed with the same reduction as sketched earlier to reduce the problem of satisfiability of the two-variable logic with two linear orders to the emptiness problem of these automata. So this way, we get the following results: that the following problems are decidable. This is the problem that I just stated. But actually, the method gives us more, because we can, instead of having two linear orders, we can say that the other order is the ancestor relation of the binary tree, of the complete binary tree. Extending the observation of Rabin, we can observe that any tree order embeds in a way into the binary tree. So what is a tree order? A tree order is a partial order with a property that for any node x, the upset, so the set of ancestors of x, is linearly ordered. So this is a tree order, and any countable tree order interprets in the complete binary tree. So with this fact, which requires some proof, the two-variable logic with one linear order and one tree order has decidable satisfiability. Now we're talking about general satisfiability, and the way we solve it is by considering countable satisfiability, which is equivalent to general satisfiability. Actually, we can add even more using the power of register automata on trees. Namely, we can extend our structure by arbitrary relations which are definable in the tree order. So for example, we can extend it by the successor relation in the tree order. Using those results, we can prove satisfiability of existential second order logic with a linear order and a tree order. So this gives a sketch of the reduction of the satisfiability problem to the emptiness problem for tree register automata. So just 2 words about this latter problem. So we consider those tree automata with this Extrema constraints. They process infinite binary trees labeled by data values from the reals. And in their registers, they can store data values from the reals and compare them for inequalities, as well as compare them to the supremum or infimum of the values in the current subtree. And these automata have, as usual, a finite state space, apart from the registers which can store values from an infinite space. And basing on those states, we can define a parity acceptance condition, which is supposed to hold on every path of the accepting run. And the theorem says that this problem is decidable, and the way we do this is to reduce the problem for the emptiness problem for tree register automata with Extrema constraints to the emptiness problem of tree register automata without Extrema constraints. And this ends my talk. Thank you for your attention.